Okay, so welcome to Flower Monthly May. This is the 1st of May. It's the first Wednesday of the month. And so here we are once again. I'm joined here with Javier. My name is Nick. We're representing Flower here today. And we're joined by, as you would see, a lot of great people here who are going to speak to us on actually quite an assortment of topics. And so the way we've organized Flower Monthly for May um, actually is just to focus on these external talks. Often we have a bit of a time at the start where we tell you about some updates, but today we want to sort of clear out and give you as much room to hear from each of these three great groups who are talking to us about a variety of topics. And so as you can see here on the agenda, we've got three invited speakers. We have Viktor as well as Andreas from Scaleout. And so we're going to discuss this great collaboration between Flower and Scaleout that I think can be really beneficial for the whole community. So we're going to kick things off by talking to them. We're going to see a demo and dive into this collaboration in a bit more detail. And then after that, we've got Zaid. He is a PhD student at Rice, and he is working in a very timely and interesting area. And so it wasn't too long ago that this breakthrough in neural radiance fields really set the world afire. And we saw these great visual demos. You could do crazy stuff, these sort of walkthroughs through 3D environments from a couple of images. And then the trouble with that is that it was all based on centralized training. And so we all know in Flower and federated learning that that's a bit of a dead end. And Zed has showed us the way forward in this particular area and how you can build these neural radiance fields in a decentralized manner. So he'll be speaking to us about that. It's a great piece of work. And then we will close things off with Alessio. He is a postdoc at the University of Messina. And he's going to be talking to us about a particular really fascinating implementation of homomorphic encryption that he's managed to pull off within the Flower framework. And so now we all know that depending on the type of data you need to use, you need to think very carefully about the level of protection you provide to it. And so this provides us with another sort of key technique, a nice open source approach to homomorphic encryption that anyone could use depending on their needs. And he'll be ending things off for us. So that is the agenda for today. Let's dive into this first topic. And let me tell you a little bit about the Scaleout collaboration, but I'm going to hand over mainly to Viktor. And so our thinking is what we need in the world of federated learning is a lot more interoperability so that we can see fast adoption. We can see bigger and better forms of federated systems being developed. And what we want to provide, particularly from Flower, is for our Flower users to have a wide variety of tools available to them. And so now, with this collaboration with Scaleout, we're going to allow people who are building against the Flower APIs, people who are building Flower clients, the ability to run these in the variety of Scaleout deployment vehicles and types of frameworks and so on that have been built by these great folks at Scaleout. And so we think this can lead to people building federated systems that could not be literally built before without this collaboration of Scaleout and Flower. So I'm going to turn over to Viktor. He's going to tell us more about it, tell us more about Scaleout. We see this as the first step towards a broader collaboration, but this is an important step where we can see the initial client being able to be deployed, and then we can start to move forward from there. But Andreas is also here from Scaleout, and so I hand over to Viktor so he can start to tell us all about it. He's going to show us a demo, and at the end we can have some discussion, also including Javier. So thank you, Viktor, for joining us and being able to tell us more about this exciting step.
Thank you, Nick. Happy to be here. I'll take the screen. Okay, so my name is Viktor. I'm a machine learning engineer at Scaleout. I focus on privacy questions in FL, and I've also been working a lot with this collaboration between Scaleout and Flower. So I'm going to start off with a few slides here. I guess most of you know what Flower is. I'm going to tell you a little bit of what we are focusing on with the FEDn framework. So it's a framework similar to Flower. It's made for federated learning, but we are putting a large emphasis on truly distributed federated learning. So the goal of our app FEDn is to take projects from R&D to production. So we want to make this easy and want to make it scalable and robust. FEDn consists of two parts. We have the SDK, which is open source. This is where most of the FL code is, and this part is organized, and we're trying to make it secure and good. But you can check this out on our GitHub page. Also, we have our managed platform, which is not open source, but we want people to use it on-prem still. And this is designed for production. So you can host this entire setup with Kubernetes, and it consists of many different services and parts that is used to organize this FL thing. And how this is different, I guess, from the flow of FEDn differs from Flower is mainly two things, I guess. We have a REST API where we can get tokens or JWT tokens for clients to connect with, and we also allow for, or we have this reduce combine topology where combiners are used to aggregate, so we can allow horizontal scaling with this and have a lot of clients, I guess. And yeah, we're trying to do Scaleout plus Flower. I guess Scaleout and Flower talked, and we realized that this would be a great effort to unite the FL community and allow Flower users to use what Scaleout has to offer as well as what Flower has to offer. So I'm going to jump into a little demo of what we have done so far. We are done with the first step of this integration layers that we're trying to build. So what we can do now is we can run Flower client server apps inside of FEDn. And the next step is going to be to also run server apps in FN, but you will hear about that in the future. But this is the first step, how we can do it. We have a Flower client here and a client app. And here we can import this client app into our FEDn client, the entry point for the FEDn client. We have built an adapter for the client apps, which translates, or it calls the client app object and translates the results back from calls to the client app back using Flower code, and it goes back to generic results, which we can use in this entry point. So we have some code here in the adapter to just translate messages back and forth between what Flower uses and what FEDn uses. Now we can use this in our FEDn functions to just get the results from the Flower client. So we can train and validate and just send it back to the FEDn app. We also have this FEDn, I guess depends on this environment file. It's going to be used by the FEDn backend. And if we add this flower flag to FEDn, then it will add the flower dependency as well to this. I'm going to show you how we can run this using Studio. So first step of running is to upload some things to Studio. So we'll start with building a model. So we'll initialize a model and build initial parameters. And then we're going to upload these initial parameters to Studio, which is the managed platform. To do this, we also need to install the dependencies, and this happens automatically here when we build. Meanwhile, we can. So we have. I have prepared a project here already. It's just to start a project. We can actually begin by getting this. So this is how you call the REST API and get a discovery token here. And we can just add this to a file here, client.yaml. We add this token, and this token is going to allow the client to connect to Studio. And now we have built the initial model parameters. We also need to package the client code, so we can distribute this client code out to different clients as well. And we run FEDn package create, give the path to where the client code is, and this just packages the client code. The next step is to upload this. So you can do this either through the UI here on the web page, or you can connect with an API client, which I'm also going to show you. But let's begin with just uploading here. So we upload a package, which is the code for the client. We also need to upload a model. And with that done, we can actually start our first client. So here we add this client.yaml file, which we have the token in. Start the client, and it's going to install the dependencies and then run the client. Actually start, since we're on the same host here, so we're on one device, we can use the same token to connect with multiple clients. So we can add another client as well. Since the first client is on, we can start a session. We can just do 2 rounds here, I guess, to begin with. And you can see that this first client is the training. This one is still downloading its dependencies, but it's going to join in on the next round. And here in the Studio, we can see that we're going to get models added here. So there's the first model, which is the aggregate from the one client. And can also see here, this is, I've swapped out models here a few times. So this is from earlier training, 14 rounds. And then just now we added a new client. So it's, or new parameters. It's back to 0 again. There you can follow the performance through multiple sessions that you can run. And yeah, that's 2 clients running. So can also show you how to use the API client to start sessions or fetch information from the studio. So to do this, we need to first add a access token. We need to add this to our environment variables with FEDn auth token. After that, we need the host. We can get from the dashboard here, we can get the host to the controller. And from any Python instance, we can do import the API client. And add the host. Need to set secure to true. And from here, we can also use this API client to get models. Get a bunch of information there where you can just fetch and read whatever you want. You can also use this API client to start sessions, for example. Oh. Start a session. And this client's going to start again. So I guess that's what I had for on FEDn. So now this is the initial step. We can run ClientApps, and in the future we want to run whole Flower project, so or Flower ClientApps and Flower server apps in FEDn. I think that's going to be very cool. So that's all. Thanks.
Yeah, well, thank you for that demo. It's great. I mean, people do a lot of talking, I think, in the world of machine learning, but it's important that people actually start to deliver on some of the discussions. And so there's been discussions about, the need for interoperability and the, allowing people to combine different tools, particularly in the world of federated learning, where the whole idea is to enable people to assemble what is normally disjoint and inaccessible. So it's kind of an obvious place that you need these sort of things. But so often people just talk about it and never make it happen. But we've had a great experience working with Scaleout, and you guys have made it happen working with us, and we have a live demo. So it's critical. Thank you.
Yeah, I agree.
Javier, do you have any, I don't know, reflections, comments about this?
Yeah, I mean, I think main reflection is that I'm quite excited to see that, well, that we managed to start this collaboration, and now you can run all your usual Flower clients inside the FEDn framework and take advantage of the, the dashboard that Viktor was showing us. But I have one question that maybe I missed understanding when we were working on the collaboration. When you are, for example, installing the clients, when they pull the dependencies and all that, where are these dependencies being installed? Are they in a new environment only for that particular client, or can you maybe describe a bit more how it works? I think would be also interesting for others.
Yeah, for sure. That's actually accurate. So it's a new environment that gets created just for that client, and then it gets deleted when the client is done, or when you stop the client. It's a new way that people are starting to do this kind of thing, I guess.
Okay, interesting. And regarding how to load the data, for example, that a client has to use, that is done, is there a FEDn component doing that, or is loaded at the same time you load the Flower client?
So in this code that we have here, the data, typically for FEDn, the data is decided by yourself, but with this adapter that we built and the entry point, we're using the Flower client ID. So that gets sent from through the adapter, and you need to inject the client ID to clients as well. But there's information on that in the example on GitHub. But we use Flower datasets and client IDs to distribute the data.
Okay, so load data, the function load data is using Flower datasets, you're saying?
Yeah.
Okay, cool.
Andreas, I see you raise your hand.
Yeah, no,
feel
sorry,
free
I
to
just
jump in.
Yeah, sorry, I just wanted to jump in and also answer your. Yeah, I think this question about environments is interesting. It's a quite new feature in FEDn, and it's quite flexible. So the default is that you will pre-build the environment, but you can also then configure it so that you like reuse it, or you can also like skip the building of the environment and have a pre-built environment if you have a Docker image. So I think actually like I don't know if either of you have used MLflow at all, but the way we do it is quite inspired by how they manage projects. To the point that we actually like use some of the MLflow APIs for doing it.
Interesting, yeah. I've only used like the most basic features of MLflow, so probably I didn't see that part.
Let's take a couple of questions. If anyone in the room wants to ask some questions, just raise your hand. I'll take a look on Slack to see what I can find. Here's an interesting question. It's saying that really love this idea of federated learning, new to the space, and they want to know what would be sort of your favorite FL application. So I guess directly to the Scaleout folks, maybe it could be something you've seen some users do, or something that inspires you, or something. But this person is sort of new to FL and is wondering what's your favorite kind of use case.
Do you want to take that, Andreas?
Well, I can say mine, and maybe if you have one, you can also add it to it. No, but I think that there are, of course, many cool things. I mean, on a personal note, I have a background in biotechnology, long going back. So, like one of the applications that FEDn is used for is Swedish hospitals training brain tumor segmentation models, and this is an application I guess we have seen in different international communities, and there's one in Sweden as well doing it. And I think this one, of course, is I think really nice because it's clearly like an area where progress in AI is going to be completely blocked by data sharing issues, at least in Sweden. So it's illegal to move data outside the hospital walls in the Swedish system. And so that one I really like actually, and that we managed to progress it to patient data. I think, yeah, but there's several cool ones as well. I really like the cross-device things as well from a researcher perspective. I'm also like a university professor, and initially, like I really like this kind of challenge of scaling to millions of devices. But if I had to pick one, I think is this medical one that I think is feels very good.
Victor, how about you?
For me, it's I worked a lot in the automotive industry, so that's the one for sure for me. I worked closely with Volvo here in Sweden, and I think one of the challenges they have is that like the data distribution is constantly shifting. So it's really difficult to have fresh data to train models for cars. But with FL, we can just use new incoming data and keep improving models. That's one I really like.
Cool. Let me see if there's anything else. Oh, this is interesting. I guess it's asking any kind of insights or reflections on designing a framework. So I guess there's lots of different sort of frameworks out there, but maybe in the construction of this one, you might have had an interesting design decision to make, or kind of a perspective on how it could be anything, I suppose. It seems like a very general question, but they're just wondering, given you've built this infrastructure up, you might want to comment on some interesting design decision or user experience decision or something in the process.
Absolutely. So maybe I can take that. We're quite new in Scaleout, Victor. But yeah, so I think one of these kind of very early things that we did when we started, we decided from a design perspective that there shall be no open ports on the clients, which I think was very important. That's kind of critical to run it in a real world setting on a hospital, for example. So that was kind of like a big decision that essentially precluded a lot, or at least would make, for example, peer-to-peer systems very hard. So like opting for like a more traditional server client architecture that was kind of steering in that direction. But then for us as well, we made this early choice to make these, we call them combiners, like they are aggregation servers in the FEDn framework, to make them as stateless as possible. So we wanted to have a tiered architecture. And that's what we realize now, but I think also like moving forward, like going for this kind of hierarchical approach to federated learning, we think is quite interesting and has a lot of potential in cross-device learning. So currently we have like a tiered architecture where you can scale, you can have an arbitrary number of aggregation servers that can be geographically distributed. There was also like a design choice that of course added quite a bit of complexity early on. Sometimes I joked like with the team that we have, our scalability is ahead of federated learning maturity. But in the same time, it was also like a very interesting thing to work on. So I think those two were quite early decisions that I think had a lot of influence on our development. I would say, yeah.
It's really interesting. It makes me think of perhaps one of the things we can explore together would be to look at building some sort of hierarchical FL system where we could use this interoperability. Given that there seems to be an over sort of attention to these very flat topologies, whereas you can really kind of think and see some of the value from FL of stitching together relatively large separate FL systems. Maybe for this hospital scenario you mentioned earlier, it could be a whole Swedish infrastructure, and maybe the UK. We could finally have a bit of
exactly. That's a very good point, because it also adds another level of security that you can you have like a local aggregation going on. I think that's very good. We should look into that, I think.
Yeah, it's funny that people that really haven't looked into that much. There's so many papers that look at this very flat, but I mean there'll be other additional issues to explore once you have these systems. I'm sorry I interrupted you though.
No, I just a general comment as well on what you said in the introduction there about interoperability. I think you and I both have academic backgrounds, and I'm sure you have also seen in past work like how premature standardization in mature R&D fields can actually be quite harmful. There's advantages, but there's also a lot of potential harm in driving research towards a certain state or a certain. I saw this a lot when I worked previously in systems biology, for example. it helps, but it also limits the way people think or the way new algorithms get formed. So I think I'm really happy about this collaboration. I think this is like a good sort of level to facilitate for the user to try to reduce fragmentation in the landscape without sort of premature standardization. I think that's really good.
No, I agree. I think it's still we're still very early in this situation, and so we might not even know some of the main problems that we'll encounter until we start to really build and see some of these things happen.
Exactly.
So yeah. Well, thank you so much. It's a great collaboration. We're going to keep on pushing forward. We're going to make this the compatibility more seamless and kind of give users great choices to build the systems they want to build. Yeah, so thank you so much.
Thank you.
Thank you.
Great.
Thank you, Viktor.
Thank you.
Great. Well, we're going to move on to our next speaker. So our next speaker is Zaid. Zaid Tasneem from Rice University. He has done a really interesting piece of research here on how you can train neural radiance fields with decentralized methods. So I'm going to hand over to him. He can tell us all about the paper. This particular piece of research was done with Flower. And so, yeah, we're happy to see people benefiting from the framework. So over to you, Zaid.
Thank you, Nick. Let me share my slides first. And also, I'm so happy that while working on my problem, I got to use Flower because it really solved like a huge part of my research. So let me start with, can you see my screen?
Yeah, it looks great.
Okay, so that sounds good. So yeah, so today's talk is about decentralized neural radiance fields. And first of all, let me introduce myself. I'm a final year PhD student at Rice University. And apart from working on like federated learning, I've also my dissertation is about privacy-aware computational cameras and frameworks. So I have other works that are interested more towards imaging and how to image in privacy-aware fashion. But I think this is a very interesting problem of decentralized, computation and how we can add that into the problem of neural radiance fields. So let me start with first the problem statement. So the problem statement we defined for today's talk is, can we use personal images to learn immersive representations at a global scale? And the idea comes from this notion that there are geotagged images of millions of scenes around the globe. They are siloed in personal camera rolls. As you can see, the multiple users have visited the same one of these millions scenes, and they have taken different viewpoints of the same scene. And we have to come up with, in this talk, we have to come up with an XYZ algorithm that does immersive views of millions of scenes. So you can by immersive views, you mean that you can pretend that you can roam around in the scene as if you were actually there. So let me motivate the problem slightly more. So the question I'm going to ask is, can we render the world with high fidelity? And by the world, I mean all of the world with high fidelity. So imagine sitting in your living room with your $3,000, Vision Pro headset, and let's say you want to virtually travel the earth. You want to go to Boston. You want to basically see what the streets of Boston is like. You want to move around them, walk around them, see how they're like during night. You want to walk into a restaurant in Boston, and you want to kind of experience sitting, in your couch, how the world feels like. So how does it happen? As Nick had mentioned earlier, there's this powerful new algorithm came out a few years ago, neural radiance fields for 3D representation. And all of the previous renderings were created by some version of this NeRF algorithm. And so basically what are NeRFs? NeRFs are multi-layer perceptrons or neural networks that take a bunch of images of a scene and they try to learn a representation of that scene. So in this case, there's this scene on the left, which is a Lego excavator. And then the idea is that what the users have or what the people have are just the image views, the images that people have captured. And what the algorithm does, it basically renders per pixel a ray that shoots across the scene volume. And from that, this neural network is queried for different points along this ray. And the neural network has to predict the color and density at each point. And you do it for all the rays in your images. You sort of basically can plot the PDF distribution, which is basically color. You can see the color showing up in the PDF, plus also what is the density of points along this ray. And then you can implement a very fast volume rendering algorithm that sort of converts this like ray PDFs into like what the pixel value should look like for that particular pixel. And since you have the images already, you know what the ground truth pixel value should be like. So you take a rendering loss, which is just an L2 loss, and then that way you can learn the neural networks that represent the 3D scene. So NeRF algorithms are basically like, recipes. You can take basically that take a bunch of ingredients, and the ingredients in this case is a visual data as input. And they can, also be served on different platters. So, rendering is also a problem in neural networks. Once you learn these NeRF algorithms, how do you render for, final applications like on your Apple Vision Pro headset or your mobile devices? There's a lot of work that goes into both the aspects of NeRF algorithms and rendering, like that handles constraints like computing, storage, and how do you learn with only few shots, and if you have inconsistencies in your images. But not a lot of work is done on the ingredients of the dish itself, which is the volume and diversity of data that can be used. So the more the volume you have, the more scenes you have, the more NeRFs you can create. And also, because you're going to use these data now, privacy concerns come if you end up using users' personal data. So let me just talk about what are the sources of visual data. So some are public images on the internet, like people always post where they're out, where they're like visiting on Instagram, Facebook, and other avenues. On the right, you can see these are some curated images by Google Maps about this particular bar in Houston, Texas, and basically you can see there's a bunch of images it has. But the interesting part about public images is that only 2% of the data that we actually capture, 2% of all the images that we actually capture on our phones, and end up on the internet. The rest of them remain siloed in our personal devices. There's another form of data which is enterprise data. So Google is always trying to send out this Google Maps card that trying to collect data across the world. And then also they send out people with the backpacks having camera rigs on top, and sort of collect more and more data about the world. So this is good, but at the same time, it's very expensive because these sensing devices cost a lot, and then sending people out and drivers out cost a huge labor cost. The last one that we have not actually looked into, which is private user images. So everyone has a camera phone, and on average, we take around 2 to 3 images per day. We don't share it on the internet. People usually keep them private, and they end up either on the Apple and Google Photos app or just their camera galleries. So what can we do with these images? So what do these images contain? The camera rails contain geotagged and time variable images. So on the left, you can see user one's Google Photos heat map, where they have visited this particular bar, as I mentioned earlier, on 16 December in 2021. And on the right, you can see another user who has also visited the same bar, but on a different time. Now imagine having millions of these users for millions of scenes, and what can we do with these scenes is the problem statement we had. So yeah, we have to come up with this XYZ algorithm, takes these kind of users, their data, and create NeRF renderings of those scenes. But then what should be the key requirements of this XYZ algorithm should be? So one should be photorealism, because you're trying to sort of create the same world back. So it has to be photorealistic. Second, because now you're kind of using people's personal camera rolls. So privacy concerns come into the picture, and you have to be really, really cognizant of those privacy concerns. Third is scalability. And this is where the decentralization aspect comes into play. As Nick has mentioned, you can sort of do these centrally. You can try to learn all of the scenes, scenes centrally, but at the same time, you end up spending a lot of compute on your own. So how to scale up to millions of scenes, how to make sure when you scale to millions of scenes, how well does your algorithm scale up? So I'm going to mention again the challenges of learning now some personal images. So the challenge of privacy. First is the challenge of privacy. So user images may contain personal content that users are hesitant to share publicly. As you can see, in this user image captured on a personal device, it features both scene-specific global content and the one that we want to actually render, and the user-specific, such as the monument, and user-specific personal content like the individual captured in the frame. Secondly, as I mentioned, learning nerfs from millions of scenes in a centralized fashion is computationally intractable. Training a nerf for a single scene requires like 100 teraflops of computing power. Depends on the scene, but usually that's the average figure. And performing these computations centrally would not scale for million scenes because you require like 100 million times more of this compute. This is where a privacy-aware decentralized approach, which I introduced right now, DecentNeRF, comes into play. It can create photorealistic renderings as shown in this video without requiring users to share their raw personal data with the server. Furthermore, DecentNeRF demands 4 orders of magnitude less server compute per scene, making this solution scalable for learning nerfs at a global scale. So before we present DecentNeRF, let's look at some possible solutions and why they don't work. So in this case, you have multiple users, they have gone to a particular scene, they have, images from multiple viewpoints on their user devices, as shown in the left. The problem that we want to address is like there's a server that wants to create a nerf using these user images. So the obvious solution is centralized neural network fields, which is like send all the data onto the center server and sort of train a nerf algorithm. And you can see the nerf algorithm, is like photorealistic. It looks, kind of reasonable. But at the same time, because you send all the data onto the server has basically seen all the images that you have. So it's not privacy agnostic. So it's not privacy aware. And the third thing it's failing at is that for one scene it works, but then if you go for like millions of scenes, then you come to the same problem of scaling. So centralized solution might not be the best solution that we want. The second thing that folks over here especially would mention is like, oh, why don't you do federated neural radiance fields? So these actually exist, but then they don't actually work in real life. So what in federated learning happens is that instead of sharing the data, you share either representation of data or like some neural network that learns a task on the data. So you basically share that user neural network with the server, and then the server can you send it, the server sends it back. You keep doing this back and forth of taking the average of the server and then relearning like locally on the local device. How does it well? And then you can see this nerf aggregated on the server, learned using federated neural network fields, doesn't work that well. The reason being it's not photorealistic. A lot of a lot of personal content starts showing up. Secondly, it's also not privacy aware because even though you've only sent the representation of the data, that data, the 3D scene data itself contains like personal content, and you have not made sure that you have taken all the personal content. But the good thing about it, it's decentralized. So in this case, all of the learning happens on the user side. So all the training cost is borne by the user, while the server only bears the cost of just aggregating these MLPs together. And these could be very minute compared to what the training cost of actually learning a nerf is. So here we introduce, DecentNeRF. It's a 3-step approach, drawing concepts from nerfs like personal global separation, from security like secure multi-party computation, and also fair learning, like trying to optimize what the user weight should be for the global model. So first, we present the first key insight that helps us, achieve this thing, which is one is personal and global content can be separated. So you can see that in this particular user image is like highlighted by in red. The personal content is there, but what you notice is that personal content is transient across users. So this personal content would not be like sort of available in user devices because this picture was taken at a different time. While the global content is static across users. So global content would be there no matter which user comes and takes an image. So it's going to be static across user. So what we do is we employ 2 MLPs. One MLP, one neural network, basically captures the personal content and the other captures the global content together. We do it for multiple users. And in this way, we sort of only share the user's global MLPs. So this way, only the user global content gets shared to the server, while the personal content remains local to the user devices. Another thing that we notice is that data is heterogeneous. We talked about in federated learning, like IID, non-IID, does it work for IID settings or does it work for like non-IID settings or not? So in general, in like real world scenarios, data is always like, non-IID. So the users can vary in terms of like, number of views, number of disparity, user to scene content, like maybe one has a lot of occlusions, one user doesn't have a lot of occlusions. So instead Unlike typical federated learning, where each user's contribution is like, let me go back. Each user's contribution is like equal, as noted by the equally weighted arrows towards the server global MLP. We can sort of come up with introduce a novel federation procedure where the per user scaling is learned implicitly to maximize the visual fidelity. So we call it a learned federation of global MLP weights, and it improves pluralism. And the way it's learned, and I'm not talking about this slide in this like talk, but basically, if a user performs very well on its particular task of rendering its own content, then we start valuing it more and more than other users who start failing on their rendering performance. The key insight number 3 is that basically the user global MLP has personal content. Even though we do the separation on the device itself, we found in this particular graph that in the initial rounds, here you can see on the y-axis the personal content measure in terms of PSNR, and over the x-axis is the federation learning rounds. How over the length of aggregation, how does it perform? And in the blue you can see the user global MLP. So a particular user, let's say the blue user on the top left, that's the user that we're trying to see. And then you can see initially it has a lot of personal content, but then overall it starts reducing its personal content, and the personal MLP starts capturing that personal content back. The reason is that initially all of the users would not know what is global or personal because they don't know what the other users think is personal and global, and that only happens due to aggregation. So in the initial rounds, even though the global MLPs from the user side might leak information, we want to use something like secure multi-party computation to prevent the server from accessing these individual users' MLP. So the key idea over here is this: is if the server can see the individual users' global MLP, it can know what the personal content is, but the user can only see the average out global MLP. So aggregation of all the users' global MLP. And now in this case, you get an average MLP, and that average MLP doesn't leak out information as badly as the individual MLP. So this is what the decentralized DecentNeRFs looks like. Again, 3 different approaches, 3 different key innovations: personal global content separation, using users of secure multi-party computation for maintaining privacy, and then learned federation of global MLP weights to improve visual fidelity. So how does it look like? In terms of privacy, so privacy in general, people try to define it in a binary term. Something is private or not private, but then in theory, it's kind of like a gray area in terms of how do you measure privacy, and it depends on what application you have. So in this particular case, we measure privacy leakage as server's ability to reconstruct the personal content. You can see for a centralized NERF, because the personal images are shared, you can server knows exactly what the personal content is. For federated NERF, even though we're sharing the representation, from the representation itself, we show that we can sort of reconstruct what the personal content looks like. So in this case, it's kind of does you can't really say who the person is, but you all know what the person is doing. They're raising their hand, what they're wearing, all of these privacy details get, shown out. But in our case of DecentNeRF, we have minimal personal content rendering. So even in the first initial rounds where the global content was very high, we see in the average MLPs, there's no personal content at all. And this is also verified by running a person detection across all the views of all the training views across all different federation rounds. And you can see federated NERFs, the personal content, number of person detection done on these images by a person detection network improves. But for DecentNeRF, the value is very, very minimal, almost 0. It's also scalable. So here we're going to talk about how DecentNeRF learns photorealistic renderings with 4 orders of less server compute than a centralized approach. So here you can see DecentNeRF's renderings. Here you can see federated NERF, which is a naive decentralized approach. And you can see NERF in the wild, which is a centralized approach. In terms of reconstruction quality, we do as good as a centralized approach. The PSNR degradation is not much. At the same time, the server compute we have is around 5 billion flops, which is comparable to what the naive decentralized approach would do, but much, much better than what a NERF in the wild 200 teraflops, training cost it requires. And also you can see in these areas of where personal content is present, actually ours do the best. It kind of doesn't show any personal content at all, while even you can see blobby artifacts both on FEDn and the centralized NERF. So there are some more results about crowdsourced data. Here you've taken two more, images where they're basically crowdsourced by people, and then you can see on the top, so the rightmost two like columns, you can see DecentNeRF and the ground truth performance, and you can see FEDn kind of doesn't reconstruct these features back, especially the details. Over here, this becomes very blurry, and in this case, you're able to like get more of these like details back. Obviously, these were done with like very small, like very vanilla nerves. So these problems can be like photorealism can be improved if the axis that you want to improve is photorealism. You can do much better nerf algorithms than the vanilla nerfs that I've shown this. This is also sort of like saying that in terms of photorealism, like the performance drop is not much across multiple measures of SSIM, LPIPs, and PSNR, especially considering if you were doing that for a naive decentralized approach like federated nerfs, or decentralized approach like DecentNeRF would perform much better. So again, along with photorealism, our DecentNeRF prevents leakage of personal information. It's also scalable. It requires 4 hours less server compute. But where can we use this, this DecentNeRF? So you have this notion of like geotag images on users' personal camera rolls. One thing that you can improve is like Google Maps immersive views for indoors and streets. So basically, this is something that Google itself has like said that they want to do, whereas basically you want to go to sort of like a new restaurant. You don't know what a restaurant looks like. I mean, I can look at the images, but it doesn't really give me the vibes of that place. Like, can I take my colleague for dinner over there? Can I take a date over for dinner or not? So in this case, you can sort of like, look at them in 3D and kind of figure out what the vibe of the restaurant is. So currently, how Google imagines this will be done is basically the 5 steps to it. But one of the important part is photo capture. In this case, a trained photographer goes to a venue and follows a strategy to capture these things. So what DecentNeRFs can come in and do is basically sort of come in and sort of like take the images that are available in user's personal phone, and then sort of replace this like sending of this highly trained photographer to like capture these images, and that can be replaced by just using like crowdsourced images. Another is basically this Google Maps updating. So according to Google, it's like, one of the most difficult features to keep up to date. So sort of like Google tries to take new street view photos in major cities once a year. And then if you have crowdsourced images, you can sort of like these nerf renderings can help you sort of update these maps so they don't fall behind. Another thing that you can do is sort of like you have multiple, you have multiple recordings, like, videos on your phone of concerts on different like memories that you have, and you can employ these dynamic nerfs. So I show for only for static scenes, but the potential in the future is to do for like dynamic nerfs where they, instead of just doing 3D representation, they can do 3D plus time representations. And I'm sure it for a very small scenes, like you can do it for city scale size, and then that can help you in terms of, urban planning and development. This is what I showed for my case is phototourism. So I've shown like 3 phototourism sites where you can like sort of like put on your headset and kind of, roam around roam around those things. So I want to like thank my collaborators. So at Rice University, my advisor is Shubhiragwan, and then another postdoc who is actually at MIT right now is Akshat. And at the MIT Camera Culture Group, I was working with Ramesh Raskar's group with Kushal, Abhishek, and Praneeth, Abhishek and Praneeth are very good at like, I think Praneeth and Abhishek came up with this idea of split learning as opposed to like federated learning. So they were very helpful to like, talk about it. Also, at the same time, I would like to thank Flower Labs and Javier for like, helping me out, because I think when I was starting with this project, I had no clue about federated learning, and then just having access to something that's so open source and so easy to use was really, really helpful. So that's the reason like, Flower Labs is like an integral part of this project. Okay, I'm happy to take questions now.
Thank you for that talk. It was I really appreciate the way that you paced that talk out and kind of walked us through motivation, the technology, and also the use cases. So yeah, thank you. Great talk. If anyone in the audience wants to ask a question, raise your hand. I'll check out the Slack. But yeah, let's see what's out there question-wise. Oh, Javier's got a question. Okay, over to you.
Yeah, I have, maybe it's a very easy question, but well, first of all, I really like the presentation. I think also having all those visualizations of the results make it's super nice to showcase how good your method works. So that's really nice to see. My question is about what has to change in how the framework works, so you can, for example, recover some of the details in this, in the results of the NERF. I know there are some techniques, or there were some techniques a while ago, like maybe using a gun to hallucinate some details and things like that. How do you see this? That could be done maybe in Excel.
So I think it's a very interesting question. So I think any pipeline currently with the system that I developed will take some more innovation to get in. But at the same time, you can, let's say, can give you an example of this case where you want to sort of create this, like, let's say, where's that figure? Like this vibe of this restaurant. That's the problem that you have, right? You want to create this vibe of the restaurant. But then you can see that, like, doing from crowdsourced images, it would not be possible because those would be blurred out, because the chairs would have moved in like 3 years' time. So those things, if you want to reconstruct, would not be working. So things like where you can sort of like look at one example of a chair, in one of these images, like the most current one, let's say the restaurant has not changed the chairs in the most current one, and sort of start rendering based on, like what using GAN-based methods to sort of start rendering those things instead of like trying to learn everything from the users, right? So those can come into, like, how do you say, work in conjunction rather than like, separately.
Okay, but do you see then this adding of details like a post-processing more than something that can be learned?
I think it has to be sort of post-processing, because those require some specific application. It's not just about photorealism now. It's more about presentation of the data, right? Of what you're trying to show.
And one final question regarding the model. Can you tell us a bit of how big is the MLP that is being federated? I guess maybe the global part of the model.
Yeah, so I think I have something on it. So basically, I think they're very small, like MLPs. They're like eight layers or something, with like one like nonlinear layer at the end. So they're very, very small, but they are like, so in this case, they're separated into 3 parts. One is the global MLP, which has the position part and the view direction part. And then the second is the personal MLP, which has the personal emending. And then it's basically, they are like 3 of them, but they are like very, very small. But if you increase the number of, like, if you increase the size of your thing, you have to include more and more MLPs, right? So people have shown killer nerves or block nerves, and even algorithms after that kind of like do it like a large scale. So that then you have to like either increase your MLP size or distribute your MLPs, right?
Yeah.
Also, this is, by the way, this is basically NERF in the wild, but running for one particular user. So the actual MLPs are from NERF in the white paper.
Mm-hmm. Okay, cool.
Actually, we're running a little low on time, but I'll just take this one question. And essentially, the user saying, wow, this is very cool. Can I use this now? Is it ready? So I suppose this question is more about, an open sourcing, or someone you're showing some interesting rendering here based on some images. So like, I guess it's more of an engineering question. What's left to be built out, or could you speak to some of those issues?
That's a very interesting question. I also want to talk about this because I think my perspective on this particular problem itself is that, yeah, I mean, you can use it and you can improve the NERF algorithms slightly to get better quality, and then you can sort of implement it out. The interesting issue is data. I don't think if I were to do this today as a startup, it would not work because I would not be able to get data from people that easily. But I think at the same time, like Google Maps, or like Apple Maps, if they want to improve some of the features that they have already access to these data, because the photos that you have in your camera is always shared with your Apple Photos or Google Photos map. So they might be able to like sort of come up with like technology on top of their current layers of like UI to sort of like enable like better renderings of their immersive views and stuff.
But I guess, yes, I agree with you. There's kind of a cold start issue, meaning you need enough users to be able to build these images. But from a software point of view, does the code that allows you to build these representations, does it work on a phone? Or I guess these are all server-based
Oh, okay,
things,
sorry.
or...
I think that's so basically these don't work on phones right now. So they were implemented using Flower Labs, but they actually run on GPUs right now. So what they have is what Flower Labs, Flower, like the library does, is basically separate out my GPU into like multiple clients. And now I simulate sort of these clients as like, they actually exist in the real world, but they're actually all simulated. So I think deploying them, I think this is why I chose, I think our Flower is because it's an open source library and there's like, actual implementations that, we can sort of do in user devices, but I haven't looked into it right now. So maybe something, if somebody wants to take over and like wants to do this, I think that'll be very, very cool.
But the models you've trained, the input to the models are I guess pixels, right? And then they produce this there's nothing, there's no kind of missing pieces of the pipeline that's being kind of approximated. Or
no, nothing. It's all done, but it's all simulated though. Like it's not done.
Sure.
So all the data is on my server. And this one server has like multiple GPUs, and then we can split the GPUs because Flowers let's allow that. But all of the data is sort of like, but yeah, no one user can look at other users' data. It's kind of like split in that way.
Yeah. Okay. Interesting. And did you open source the code, or I guess because just?
I think I'm about to in a couple of weeks.
Okay. That's cool. I mean, it'd be cool to see what people build on top of this and kind of start to do their own thing. But yes, yeah, great piece of work.
Yeah. Thanks a lot.
Awesome.
Okay, I think I'm done sharing. Thanks a lot for letting me talk. I think it was very interesting to hear everything.
No, totally. No, thank you for contributing. Thank you so much. Okay, let's share the screen again and transition to our last speaker. So our last speaker I met at the Flower AI Summit about maybe it's 6 weeks ago now. I've lost track of time, but it's like, time moves along. But it's the first time I met Alessio, and he actually came with a group of folks from the University of Messina, and they were wonderful people, clearly very knowledgeable about the field, and we had some great interactions at that event. But then he was telling me about some of the work he's been doing. They had some great posters at the event too to show people some of this work. And then we basically wanted to hear more because it was too good to just leave as a poster. So we invited Alessio back to tell us this time at least about, because he has a few different sort of projects from the same group. But this time we wanted to hear about the work he's been doing in the direction of homomorphic encryption and how he's been using this with Flower to kind of build really quite secure and privacy preserving types of federated learning. So thank you for joining us today. It's great to have you back. Over to you. We're fascinated to hear what you have been doing.
Okay, thank you very much. Thank you for the invitation. I'm very honored to be virtually here to show a little bit of our work. And so, okay, so let's start. I share my screen now. I'm just 1 moment. Okay, so could you see my screen, right? So thank you again for this invitation. It was an honor for me to present in this Flower monthly event. It was a very profuse experience at the Flower AI Summit. So we are very happy to show our work, and so also in the future about the poster. So thank you very much. Okay, so let's start with the presentation. So so could you see my screen, right? Can you see my screen, right?
Yes.
Yes, we can hear. Sorry, I was on mute. Yes.
Perfect. Perfect. So I'm Alessio Catalfamo. I am postdoc at University of Messina. So one of my research interests is in federated learning, and in particular also in secure federated learning problem. So we exploit Flower framework to do our research work, and so it's happy for me to be here. So let's start. Let's start with the outline of this presentation. We start talking about the secure federated learning problem, and in particular the secure aggregation solutions. So we talk about homomorphic encryption as solution of secure aggregation. We talk about homomorphic encryption from a practical perspective, and so we also see how we are implemented the homomorphic encryption in Flower in we can say in a standard way, because we would like to provide this solution, this general solution for the community in general. So we'll see the some tests, some performance evaluation about our practical implementation, and finally we'll see our future works about this direction. So, as we all know, federated learning is born to train a machine learning model without sharing raw data with a central server. So in federated learning, we have n local data spread among n clients. Each client train a local model, so train local weights and share these weights with a central server. These weights are aggregated in a central server according to a specific strategy. For example, federated averaging, as we all know, is the first strategy introduced in federated learning, in which we have a subset of clients that perform a train task and share their weights to a central server. So as we said also today in the previous presentation, it's not completely secure share local weights or local gradients with a parameter server, because some work in scientific literature proves that starting from weights or starting from gradients, it's possible to reconstruct original data. In particular, if we consider an attacker a man-in-the-middle attacker or a malicious parameter server, he has the possibility to reconstruct original data from weights, from locally trained weights, or from gradients. So in the first case, for example, we can consider the data leakage from gradients. So in this case, it's possible in federated SGD algorithm, where each client doesn't update the local weight, but it share only the gradients. So it perform only the gradients, it compute only the gradients, and it share only the gradients. So starting from gradients, it's possible to reconstruct original data. In particular, if the attacker randomly initialize a dummy sample X and Y, and so we feed this dummy sample into the architecture, into the model architecture. It gets dummy gradients. It can optimize the distance between the dummy gradients with the original gradients. So optimizing this instance with a specific loss function, with a new loss function that is different from the original loss function of client, it can reconstruct the original sample. So with a optimization, it's a optimization problem in which the distance is minimized and the sample data can be leaked. The second case is in the actual federated learning scenario. So the attacker or the malicious aggregator server gets the weights, the locally trained weights. Starting from them, some work in scientific literature design this loss function, this specific loss function that is based on Frobenius norm. And so with this loss function is dependent only by current weights, so by client weights and by also global weights. Giving only these two elements, only these two sets of weights, is possible to design, to perform this loss function, and also in this case we can optimize the loss function, minimize this loss function in order to reconstruct the original data. So the main idea is to protect the weights and or the gradients when the clients transmit them. Different techniques was proposed during last years. One example, one of the techniques proposed is the differential privacy. The other is homomorphic encryption. So differential privacy is a mathematical framework that consists of introduced controlled noise into the data in order to protect the data owner privacy. So in order to protect the data, but without change the final output of our computation. In the case of federated learning, we are talking about training over local data. So if the client introduce some controlled noise on the local data set, it's possible to train the model without the original data, protecting the original data in the local client. So for the homomorphic encryption is a term that represents the class of encryption scheme in which it's possible to perform some computation over the encrypted data. It is based on property of homomorphic property. So homomorphic property of the group algebraic structure. So if we consider the plaintext and the ciphertext do different sets, and if we consider these sets as part of a algebraic group, we can consider the homomorphism property over these groups, and in particular we can consider the function, for example, the function E from P, from plaintext set to ciphertext set, in which this equality is true. So as we can say, this equality is actually the encryption over ciphertext, because as we can say by the equality, if we perform this function E over encrypted data, we obtain a coherent result respect to plaintext elements. So homomorphic encryption is very used in cloud computing scenarios in which we have a not trusted server. So if we compute some elaboration, some computation over stored data on cloud, homomorphic encryption is very famous in scientific literature. The homomorphic encryption schemes that are all the encryption algorithm with homomorphic property, they are grouped on three groups. So the partially homomorphic encryption, in which we are able to perform a limited operation over encrypted data, over ciphertext set. Somewhat homomorphic encryption, in which we have a limited number of additional multiplication operations, and the fully homomorphic encryption that are the most innovative algorithm, in which we can compute an infinite number of addition or multiplication over ciphertext over ciphertext elements. So some of the most famous fully homomorphic encryption schemes are, for example, the Payer algorithm, that is an active homomorphic encryption, is one of the first homomorphic encryption scheme, and it is a partial homomorphic encryption scheme because it's possible only to perform some over encrypted data. Other important encryption scheme are BFV and BGV that are based on ring learning with errors problem. That is a very famous problem in post-quantum cryptography. One of the most innovative, one of the most new algorithm, homomorphic encryption algorithm, is CKKS, that is very innovative because it supports several operations over real numbers. So from a practical perspective, we can consider different libraries to implement homomorphic encryption. For example, Microsoft Seal, that is developed by Microsoft Research, or HE library, that is developed by IBM. Both of them implements fully homomorphic encryption schemes. The library that we use in our implementation on Flower is TenSeal, that is a library for homomorphic encryption operation on tensors. It is built on Microsoft Seal. It's like a Python API built over Microsoft Seal, and it is designed for efficient processing of encrypted data in machine learning application, because it is designed for, as we said, for homomorphic encryption operation on tensors. So in our implementation, we have considered a client customization and a custom strategy implementation. So in these two components, in these two classes, we have introduced homomorphic encryption operation using, as we have said, the TenSeal library. So we have re-implemented the client and strategy classes, and so we use TenSeal, as we said, because it's very convenient. In particular, it's very easy to integrate the tensor operation, the encrypted tensor operation with the PyTorch library, with PyTorch tensors. So in our work, we distinguished three main phases in which we have realized homomorphic encryption operation. So we can consider, in general, in the Flower flow, we can consider three main phases: the model initialization, that is performed by the server, that pick one random client, get the model, and spread the model among all the clients. We obviously have considered the client train phase, in which that is the actually training of the local model by each client, and the aggregation phase, in which we have also implemented the strategy, the aggregation strategy. In particular, we have implemented a encrypted version of federated averaging, and also FedProx, because the strategy is quite the same in FedProx and FedAVG. The difference is in the training, in the client training. So the aggregation phase is logically the same. So we don't perform encrypt or decrypt operation in on aggregation side, because the aggregation, the average in this case, is logically the same with respect to the nature of the data. Obviously, from a practical perspective, we have a difference. We have some differences, because we have to implement the aggregation exploiting TenSeal libraries. So this is like this is a sequence diagram of interaction between client and server during model initialization phase, and we can see that we encrypt the data of client, of chosen client, in order to spread them in an encryption in an encrypted way. Also, another important operation is the serialization of the parameters for transmission over the network from client and aggregation server. So during client train phase, we also have to decrypt and encrypt the parameters, because when each client get the global model, the global weights, we have to decrypt them in order to update them. So we have to decrypt them, set parameters in our local client model, update the parameters, and encrypt them in order to send them encrypted. So now let's give a look to some snippet of the code, just to understand what we have implemented. So this is the snippet of code to generate public key pair. Homomorphic encryption schemes are public key algorithm encryptions. So we have a public key, a private key, and we use public key to encrypt, and we use private key to decrypt. As we said, we override, we create a custom client, we customize the client object. In particular, we override the fit method in order to insert this new approach, in order to insert the decryption and encryption of the parameters before and after the train method, the train function. So where we update the local parameters, because the update of local parameters is performed on plain text parameter. Okay, so for the aggregation, as we said, we also implement the aggregation, even if, as we said, logically is the same, because we don't decrypt or encrypt parameters on the aggregation server. So we also perform some evaluation, some tests, because we want to understand how much is the overhead introduced by the homomorphic encryption. As we can say, the overhead is quite relevant, and this is one of the problem of homomorphic encryption in any use case, in any scenarios, also in other scenario outside the federated learning context. And so, as we can say from the image, from the right image, I want to warn you that y-axis is on a logarithmic scale. So the difference is quite relevant from FEDAVG and FEDAVG encrypted, or FedProx and FedProx encrypted. And so this is one of the problems. We have performed different tests in training and in aggregation. So in training, we have also compared FEDAVG encrypted and FedProx encrypted, because the train is a little bit different, because in FedProx encrypted the function to minimize is a little bit different. And so, as we said, this is one of the problem of homomorphic encryption is the overhead. So future works we have planned about this direction, about this topic. So we are publishing this work, and so we would like to extend this work with other homomorphic encryption libraries. For example, we know we met some Zama guys in Flower AI Summit, and so we want to interact with them in order to implement also with their library the same approach. we are planning to implement a Flower baseline with our work, and so we want to exploit this implementation in a practical use case. Another important point is related to the key management, because in this case we use the regular homomorphic encryption scheme, but the optimal solution in security terms is to use a multi-key algorithm in order to have different keys, different private keys for different devices. And multi-key algorithm is a specific class of homomorphic encryption schemes that enable different private key, but a unique public key. And this is the optimal solution if we work with physical devices, because in this way we must not share the same private key with different devices. So that's it. Thank you for the attention. And so if you have some questions, I'm glad to answer them. Thank you.
Great. Thank you so much for the presentation. Really, really interesting stuff. As you mentioned, we have worked in the past with Zama, and so they're really looking at how you can take FHE to production settings and really have it be applied. And so I was curious about what the main difference. I guess that would probably constitute the primary difference. I'd imagine those libraries are kind of built to be bulletproof, to be used today, and then this is more an exploration of how you would support these methods, I suppose. Is that what you'd say, or?
Yes. So with this new library, the new library, it's possible, but we should change some part of the implementation.
Oh, I see. So you're saying you could change some of the underlying pieces to their library potentially. Is that
yes,
kind of
because
yes,
because now we use the Tensor library, and so Tensor library owns specific methods to encrypt, to perform sum, to perform arithmetic operation. So with a new library, we have to change some piece of code. It could be interesting to create a solution that is transparent respect to the library used, to the backend used for homomorphic encryption. This could be a very interesting work, but so it's not simple.
Yeah, sure. Great. Andreas has a question, so over to him.
Sorry?
Yeah, hi. Nice talk, very
okay.
nice work, interesting work. I had a question about other algorithms, like if you did experiments on federated averaging. Have you also tried, is it possible to apply this to, say, FEDn algorithms, where you have to do like some non-linear computation, like on the server side? Have you tried that?
So,
yes. The question is, would you run into numerical instability issues? That's what I'm after.
So, thank you for the question. Yes, it is possible. So with FEDn, I think that the difference is that we use Adam optimizer to local update, right?
Yeah. So the local update can be Adam in federated averaging as well. The difference is that this is FedOpt ID, that you compute pseudo gradients. Like the difference on the server side is, instead of adding parameters, you need to take like the parameters minus the previous global model to get them and sum that up to get the global, like a pseudo gradient. And then you like track momentum terms on the server side. So like you need to do some sort of, it's like you need to compute some stuff, and that involves, I guess, products between tensors, power functions and such things.
Yes, exactly.
Yes.
So
do you need to tailor expand then, or to do that? This kind of worry.
Yes, it's possible, because we can perform multiply operation over encrypted tensor. So the problem is that in in the plain text approach, we can use some libraries, like, I don't know, some optimizer, some built-in optimizer within very known libraries like PyTorch. So in this specific case, we should implement like from scratch the optimizer server side, because we have to implement. We have only arithmetic basic operation over tensors. So it's possible, but it's not.
But if you need to do like a square root, for example, of a tensor, and
yes,
then you
sure.
need to tailor expand it, or how do you do it?
Yeah, sure. Yes, sure. It's not trivial to.
Okay.
I think it's possible, but it's not. Not
trivial. Thank you so much.
Thank you for the question.
Thank you.
Great, thanks for the question. Zaid, you have a question, it seems.
Hey, it was a really good talk. I could not notice but think about, sorry, I could not stop but think about this idea of like, because I use in my project secure aggregation, which is basically, I guess what's the difference I would get if I were to use like something like this? Because I think in my case, I'm just doing aggregation on the server side. So what's the benefit I would get compared to secure aggregation if I were to use like fully homomorphic encryption?
So in your case, so if I think to your presentation, I think that maybe in your case you can avoid some leakage of the data, but I don't know. I think that you can avoid the operation of rendering that you perform client side. I think that you can avoid this kind of operation in your work because you can send the local trained weights also over the original personal images. Okay, so if I think to your presentation, I remember that you perform an operation client side in order to protect personal information, right?
Yes.
I think that with homomorphic encryption, you can avoid this your global GLP, if I remember well, the element, the operation.
Yeah, the global MLP. Yeah.
I think that you can avoid this kind of operation. I don't know if it's cheaper in terms of overhead, because as I said, homomorphic encryption introduced relevant overhead. So I don't know if with your current solution, you can save time. I don't know.
I think
it's
one question
interesting to try.
I think if I have time, I have one follow-up question, which is basically doing like NeRFs, like training NeRFs on like homomorphic data is not like a solved problem also. So it could be something that could be interesting to see coming up, where you just say, I just send all the data, forget about decentralization aspect of it, but just send the data and doing NeRF renderings on the cipher text. One fundamental issue though I have with this is that even though you can sort of create these NeRF models, eventually these NeRF models are representations of the data itself. So if the data, I guess it's still, like if finally you're getting the data out with the NeRF, like, with the plain text version of the MLPs, then have you really secured anything? In my case, I'm not talking about this case, but I think in the problem that I had. Because eventually you basically are giving out data, like that's what you want to give, which you want to give some data, but not all data, right?
Yes, sure. Yes, I think that in your case, it's less, maybe it's less appropriate. But I think that could be also interesting because so you have to consider that the training is on plain text data. The local training is only for the aggregation that yes, for the aggregation that you have to implement the homomorphic encryption operation. So only over aggregation side. Okay, so the operation on client could be also performed on plain text data.
Yeah. So I think compared to secure aggregation, homomorphic encryption would not decrypt the average weights, right? So the server would never know the average weights also. It would just know the cipher text of the average text of average weight. So I think that's the benefit I think you get from secure aggregation to fully homomorphic encryption.
Sure. Yes, the aggregation is agnostic with respect to the encryption state of the data.
Thank you so much.
Thank you for the question.
Great. Well, we have run a bit over time, so I think I'll ignore some of the questions that are pending, but yeah, I think it's probably time we should wrap this up. So thank you, Alessio, for that talk. Great talk again.
Thank you. Thank you very much.
That was really awesome. And so that is everything for Flower Monthly May. It was a jam-packed session, to be honest. We had three really important topics to discuss, three great different groups presenting. And so again, I want to thank Andreas and Viktor from Scaleout for this really important first step. It's going to be critical for the community. I can't wait to see what the community builds on it, and also as our collaboration sort of gains momentum, and we can let them build more and more interesting things by combining the best of both Flower and Scaleout. So thank you guys for coming. Great stuff. Zaid, great stuff also with this Radiance fields things. I think you're really cracking it when you're showing what can be done in terms of decentralizing these methods. And I'm sure a lot of people can kind of look at the work you've done and build on top of it into all the interesting applications that you talked about. Awesome stuff. And Alessio, thank you for you really taking a look at homomorphic encryption. I think it's a critical piece of the puzzle for many of these types of systems. Offers you sort of unique properties that you don't get from other methods in isolation. And so, yes, yeah, thank you for your talk as well. That is it. That's it for Flower Monthly in May. We'll be back here for the June edition, first Wednesday of the month, but which will fall on June the 5th. We always go off at 1600 UTC. So join us then. And thank you everyone for your time today. So take care. Bye.
Bye.
Thank you so much.
Bye.
Bye.